So we just finished hopefully getting intuition for why, my initial pressure times my initial volume divided by my initial temperature is going to equal, if I change the volume or the pressure or the temperature or some combination of all of them, is going to equal my new pressure times my new volume divided by my new temperature. And once again, just remember, all of this is, pressure times volume is proportional to the amount of kinetic energy in the system, and temperature is proportional to the amount of kinetic energy per molecule. So if we don't change the number of molecules, the amount, and since by conservation of energy, the amount of kinetic energy isn't going to change unless we do some work or get some potential energy or something. These quantities, this relationship won't change. And watch the last video, and hopefully you'll get some intuition. If it's still confusing, I'll make another video for you guys. Now, before I apply this equation, which is really, this is going to get you pretty far in thermodynamics, just knowing this, and even more, just having the intuition of what it means. I want to clarify something about temperature. So there's a lot of different ways to measure temperature. We know that in Fahrenheit, what's freezing of water? It's 32 degrees Fahrenheit is freezing. Well, that's also 0 degrees Celsius, right? And actually, that's how the Celsius scale was determined. They said, okay, where does water freeze? 0. And then where does water boil? 100 degrees Celsius is boiling. And that's how they rated it. And of course, you could be colder than the freezing of water, and you'd have to go negative in that situation. Fahrenheit, I'm actually not sure how Fahrenheit. I need to look that up in Wikipedia, or that might be something for you to do and tell me how it came out. I think boiling of water in Fahrenheit is 212 degrees, so it's a little arbitrary. I think Fahrenheit might be somehow related to human body temperature, but I'm just guessing. But anyway, you can have different scales in this situation, and they were all kind of a bit arbitrary when they were designed, kind of to just have some type of relative to scale. You could say, well, when things are boiling, they're definitely hotter. They have a higher temperature than when things are freezing. But it's not clear to say that it has, that, you have, well, you can't divide 100 by 0, but if something is 1 degree, is it necessarily the case that something that is 100 degrees Celsius is 100 times hotter or has 100 times the kinetic energy? Well, actually, we'll see that no, it's actually not the case. You don't have 100 times the kinetic energy. So this is a bit of an arbitrary scale. So the actual interval might, the interval's arbitrary. You could pick the 1 degree as being 1/100th of the distance between 0 and 100. But where you start, at least in the Celsius scale, is a bit arbitrary. They pick the freezing of water. So later on, people figured out that there is an absolute point to start at. And that absolute point to start at is the temperature at which a molecule or an atom has absolutely no kinetic energy. Because we said temperature is equal to, the average kinetic energy of the system, or the total kinetic energy of the system divided by the number of molecules, or we could say the average kinetic energy per molecule. Right? So the only way to really say that the temperature is 0 is if, and this is proportional, I should say it's proportional, because the temperature scales are still a little bit arbitrary. It's proportional, it's not exactly, it's related to. But the only way to get to a temperature of 0 should be when the kinetic energy of each and every molecule is 0, or the average kinetic. So they're not moving, they're not vibrating, they're not even blinking. These molecules are stationary. And the point at which that occurs is called absolute 0. Absolute 0. And that actually occurs, absolute 0, and that's also called 0 Kelvin. 0 Kelvin. And that is the same thing as minus 273 degrees Celsius. So nowhere in the universe, at least that I'm aware of, is it colder than minus 273 degrees Celsius. At that temperature, nothing moves, even at the atomic scale. I mean, I'm talking the electrons collapse into the nucleus. I mean, everything is completely stationary at 0 Kelvin. And it's a theoretical absolute limit. People, and maybe we'll do a bunch of videos on how you can get close to that, but in laboratory environments or maybe in deep space, it gets really close to this. But I'm not sure. I'm pretty sure nowhere in the universe do we have absolutely 0 Kelvin. at least in any place where we actually have particles. But I might be wrong there. But that's a little bit out of the scope of what we're talking about. So anyway, so the true way to measure temperature is in Kelvin. And then when you're measuring in Kelvin, if I say I have something that is 1 Kelvin versus something that is 5 Kelvin, since we kind of nail down the bottom at a point at which we really do not have kinetic energy, I can make the statement that this has 5 times the energy of this. Something that's at 5 Kelvin versus 1 Kelvin. So that whole long explanation about Kelvin, that's just to make the point that whenever we use this formula, or really any formula in thermodynamics that involve temperature, we should convert to Kelvin. Unless we're just doing change in temperature. Then you could probably keep it Celsius, but when you're doing proportionality or you're using it multiplying or dividing by temperature, you have to use Kelvin. And hopefully I made a little bit clear of why that is. So let's do an example. So let me erase. And you'd be surprised how far this takes you. And really, the main trick is just to remember to convert things to Kelvin. That's the number one reason why people miss questions on thermodynamics exams, is that they didn't convert to Kelvin. So I'm going to get a problem. This problem, and this is very typical of most of what you'll see. This is from the Barron's AP Physics B on page 226, and it says, let me see. A confined gas is at temperature of 27 degrees. So its initial temperature is 27 degrees Celsius. When it has a pressure and volume, so its pressure is 1,000 pascals, or newtons per meter squared, and the volume is 30 meters cubed. I think in one of the earlier videos, I said newtons per meter cubed. No, it's newtons per meter squared. I just want to make sure I didn't confuse people previously. So that's the initial volume. And then it says the volume is decreased. So then we go to this state where my new volume is going to be 20 meters cubed. The new temperature, it's increased. So the new temperature is now 50 degrees Celsius. And they want to know what is my new pressure. So before we just substitute into the equation and solve for the new pressure, remember, if they gave it to you in Celsius, convert to kelvins. And if they gave it to you in Fahrenheit, which they seldom do, then convert into Celsius and then convert into Kelvin. Well, we already know that 0 Kelvin is equal to minus 273 Celsius. Or another way you could say it is x Kelvin. X Kelvin is equal to, essentially whatever degree you get in Celsius, you just add 273 to it. Does that make sense? Because think of it this way: if you're at 0 degrees Celsius, you're already at you're 273 degrees above 0 Kelvin, right? Think about that. Hopefully that makes sense. Maybe you want to draw a number line just to make sure. So whatever Celsius degree you have, just add 273 to it, and you'll get Kelvin. So this is equal to what? This is equal to, let me do it in a new color. Add 273 to 27 degrees Celsius, that's 300 Kelvin. And then 50 degrees Celsius is what? Add 273 to it. So 50 plus 273 is 323. Right? So now we can substitute into this formula. So P1, 1,000 pascals times V1 times 30 divided by the first temperature, remember to do it in kelvins, 300, is equal to P2, that we don't know what that is, P2 times V1, times V2, this should be a 2 here, times V2 times 20 divided by our new temperature, 323. Let's see, we could simplify this. We could take 2 zeros off of here, take 2 zeros off of here, and then we could take a 3 out of here and take a 3 out of here, and we're left with 100. Right? This is equal to 100. Right? That was 3,000 divided by, that's 30,000 divided by 300, and so that's 100 on the left-hand side. So we have 100 is equal to P times 20 over 323. And then let me do it up here. I'm running out of time. And so if I were to just solve for it, 323 times 100 equals, divided by 20 equals, so my new pressure is 1615 pascals. And I just solved this equation, and the hard part was converting to Kelvin. See you in the next video.